because the number on Canvas is much lower than that.
Okay, so let's start. So hopefully you know, homework 1 was due yesterday. I think the numbers were 122 of you submitted, which means 20-some of you haven't submitted, taking the time that we give. I just want to remind you that only 4 days that you have slack, so, and 5 homework, so don't take all the time for this one. Then wanted to remind you that you have to submit both on Gradescope and on Canvas. So the number on Canvas are much lower, or significantly lower than on Gradescope, which means quite a few of you did one and not the other. So please go and check what you did. And do it right. 2, homework 2 is going to be out tonight, so you have 1 day to rest. And again, my suggestion is that you will look at it as soon as you can and start thinking and working. I'm going to talk more about it later today. A lot of the stuff that we're going to do today is directly relevant to the homework. 3, my office hours today is changing. It's going to be just after class. 4, I want to remind you, project. So go to the website, go to the previous slides where I talked about what is expected and what is the timeline. You have about 2 weeks, I think, for the proposals. Did we open the option for teaming? Okay, so there is an option for you to find teammates. If it's not open on Piazza, ask again. I think it should be open. It is open? Okay. Start thinking, come to office hours to talk about it. Questions? No questions. So I want to remind you to ask questions, not only now, but also after every class. A few of you come and ask excellent questions about what I talked about earlier. And I'm sure many of you would be interested in these questions. Just the fact that these questions are being asked is interesting, plus maybe the answers are also interesting. So please do ask questions. Okay, so where are we? So we talked about Perceptron last time. This is just a reminder of what is the algorithm. So we think about it as an online algorithm, really. So we take the first example, x1, y1. We have an initial hypothesis. We initialize it to 0 here. And the way I've written it here is I separated the weight vector W and the threshold theta. Most often than not, we are actually thinking about them as one concatenated vector. of dimension n+1 rather than n, because whatever we do to w, we also do to theta. And then once we take the jth example, we predict. How do we predict? Dot product w x minus theta, sine of it. If we made a mistake, if y hat is different than y, we update. Otherwise, we don't update. So it's a mistake-driven algorithm. When we do update, we update basically by adding or subtracting xi, or some product. In this case, the learning step is called eta, but basically adding or subtracting some product of xi. Simple algorithm, as simple as it can get. What did we say about the algorithm? So I'm not going to prove this, as I said, but it's important that you understand what it says and all the notation that we have here. So basically what we showed here is that if the data is linearly separable, that is, if there exists this U that separates the data, how do we know that this U separates the data? I've written it here. The dot product of U is X with each one of the examples times Y is greater than some small positive number. That means that the data is linearly separable. Think about it. Make sure that you understand that that is equivalent to saying that the data is linearly separable. It basically says, if you are a negative example, that is, the dot product U times X is negative, then the label is also negative because the product is positive. If you are a positive example, that is U dot product X is positive, the label is also positive because the product is positive. Okay? So it's just a mathematical way of writing the data is linearly separable. Moreover, I can always choose this gamma as the smallest value over all i's of this product. Because I said everything is positive, I'm going to choose the smallest positive number that satisfies this. Later on, we're going to call this margin, or something like this is going to be called margin. It basically is how far the examples are from the linear separator. And if this exists, then we said that the perceptron is going to stop making mistakes. So tying it to what we said earlier, it's somewhat magical because the perceptron searches in an infinite hypothesis space. Nevertheless, it stops making mistakes after some time. That's one. Two, it stopped making mistakes after something that is inversely proportional to this gamma, which you want to think about as the margin or the complexity parameter, the difficulty of this problem. Question on this? Notations, everything is clear. Okay. That's the proof that you can go over. Okay, so at the end of last time, we talked about a few extensions, and I want to repeat this one because it's important to understand this term, at least. What does this say? This is a slack variable, and it represents max between 0 and this gap, this difference. And again, remember that if y times the dot product wx is greater than gamma, which means the points are outside this dashed line, we are in a good shape. But then this is negative, which means all this term is 0. If we are inside this dashed line, or a red point actually moved to the other side, like you see here, then this is some positive number. And this one is going to grow linearly with w dot product x. So this basically reflects the extent to which we are deviating from the linear separability. 0 if we don't deviate, otherwise it goes up. And what we said here is that Perceptron is going to be okay even under these conditions. You're going to stop somewhere, and it's going to make mistakes, but it's going to scale nicely with how much it deviates from being linearly separable. And you're going to see this in your homework. You're basically going to look at some noisy data, which means we took some red points, moved them to the purple side, purple points, moved them to the red side, and you will see that Perceptron learns okay. And in fact, all the algorithms you'll play with learn okay. Okay, so that's one step. I'm going to skip this. We talked about it last time. A few extensions. So the key extension that we need to talk about, and we're going to talk about it for the next few weeks, different ways, is something that is called regularization. Basically, the idea that we want to learn simple concepts, simple functions. Before that, I want to say one other thing, which, again, I talked about last time a little bit, sometimes important. So Perceptron gives you a real number. The prediction is a real number, right? It's the dot product, W dot product, W transpose X. That's the output of Perceptron. Sometimes you want to interpret this as a probability distribution. If you take this dot product X and put it into this function here, 1 over 1 plus E to the minus this dot product, you'll get a number between 0 and 1. I showed this last time with the graph of U of X. Go back to the slide and verify that you agree. What you can do is you can play with this A here, this constant A that I point to here, and tune it so that it's not only between 0 and 1, it actually behaves like a probability distribution. That is, when you get the value 0.8, the probability that the prediction is 1 is 0.8. If you get the value, the dot product gives you 0.7, the probability that this is really a positive example is 0.7, and so on. So this is something that can be tuned, and sometimes you want to do this. Okay, a few other exceptions, extension that we want to talk about, we will get to later. I want to talk about one of the key regularization ideas, and we talk about it in the context of Perceptron. So we call the algorithm, which is a modification of Perceptron. So no one wants to run vanilla Perceptron. It's a good algorithm in principle. In real life, you don't want to run it because there are better versions. Here is one of them. So let's think about running Perceptron or any online algorithm. You get an example, you learn, you update or you don't update, you keep on going, you get the second example, you made a mistake, you update, and so on. Now, the way we quantify the performance of Perceptron is based on how many mistakes it's going to make until, say, it stops making mistakes. There's some unsatisfactory issue here, which is we don't know when we're going to make the mistake. The type of guarantees you really want to have is promise me that if I see 1,000 examples and train on 1,000 examples, after that everything is going to be okay. The probability of making an additional mistake is going to be small, below 5%. That would be a more satisfactory guarantee, but that's not what we get from Perceptron, right? They just tell us, don't worry, you're never going to make more than 127 mistakes, but you don't know when. So let's think about it this way. So let's assume you train the Perceptron. You train it over 100 examples, made a mistake, corrected the hypothesis. Kept on going, ran over 10 examples with no mistakes, no change to the hypothesis, made a mistake. change the hypothesis. Another one, a stretch of 128 examples, made a mistake, and so on. After your 1,000 examples, you made a mistake, you corrected it, and then you ran for 500 examples, and that's it. You don't have more examples. But the last one, you made a mistake. So you just corrected, and you're done. Which hypothesis are you going to use tomorrow when you have to use the hypothesis and predict with it? So the way I described it, you had many hypotheses in the course of learning. Let's just focus on the last three. When you got to your 1,000th example, you made a mistake. You corrected. And then you ran with this hypothesis for 499, say, examples. No mistake. You didn't update. Then the 1,500 example was a mistake. You corrected. And then you got tired. That's it. Two hypotheses to consider. The last one and the next to last. Which one would you use if I ask you tomorrow to use your hypothesis and predict on some new examples? Yes?
Probably the one before the last one, because I guess you can assume that those 400 examples that you had, constitute like the average type of question you'll be given. And the last one could just be an outlier, so you might, just overfit.
Any other suggestions? Yeah.
Why don't you use the one that gave you the most information, which utilized the most information available to the largest sample?
The last one, you mean?
Yes.
So that one argument says, I'm going to use the last one because I used all the examples in order to reach it. Another one says, the one before the last ran over 499 examples with no changes, which means on these 499 it was very good. It gives me some confidence that on a large sample, it's solid. Yes?
You could wait them and give more credit to the earlier one because it was more validated, but you give a little bit of credit to the last one.
Okay, so that's actually what we're going to do. Thank you. But even before that, I want you to think about this intuition. So the last one might be unstable because it's just one example. I changed a few. Maybe it was an outlier. Yeah.
Did you rerun both of them and see how them do on all of the training data?
Go back to the beginning and run all of them. That could be an option. But in principle, now I need to choose something and go with it. So I would choose the 499 because it's more stable. So the intuition is that what I see, the examples that I see are a sample from some distribution. I don't know what distribution, but I have to believe the sample. And really, if I'm consistent with a lot of examples, I should be happy. The last one could be some kind of an outlier. So being consistent with more examples is better. Now, ideally, what we want is the expected performance to be quantified in terms of number of examples that we've seen rather than number of mistakes. And this is what we're going to do next week when we talk about the PEC model. But in fact, every mistake-driven algorithm can be converted to a PEC learning algorithm, modulo some extreme conditions that we won't care about, in the sense that we can take a mistake-bound algorithm and make it an algorithm that gives us some global guarantees. By global guarantees, I mean here, I promise you that if you've seen M examples and you were consistent with these M examples, the future is going to be good. I'm going to give you guarantees that you will make very few mistakes as a function of this M in the future. How do we take a mistake-driven algorithm and convert it? Basically, the protocol that we discuss now is going to do it. So anyone wants to articulate it? Let's assume, I promise you, here's an algorithm that is going to make no more than 500 mistakes. It's inside this box. But I don't know when it's going to make the mistakes. I want to convert it to an algorithm that is consistent with a lot of examples, that runs with no mistakes. So for example, let's assume that if your algorithm runs on 1,000 examples with no mistakes, I'm happy. Because if it ran on a sample of a size 1,000 with no mistakes, you know that the future is going to be good. But this is not what I have in the box. In the box, I have something that is guaranteed to make up to 500 mistakes, no more than 500, but I don't know when. So you see the issue here? I have a box, I have an algorithm that is mistake bound. I don't want it. What I want is a new algorithm that has the following guarantee. If you run over 1,000 examples, I know it's going to be okay. How do I convert this box to an algorithm that runs continuously over 1,000 examples? You see, if I take the box and run it, I don't know that it's going to make, that it's going to be consistent on 1,000 examples, right? Yes?
Based on the name, I imagine that you run Perceptron several times and then average results.
Yes, how do I do it? Give me a scheme for now, just to solve my problem. I gave you in the box an algorithm that will never make more than 500 mistakes. And I want you to give me an algorithm that runs consecutively on 1,000 examples and makes no mistake. Are you guaranteed to have one even? Let's try. Take the algorithm in the box and run it. What's the worst thing that can happen? Let's say it makes no mistakes, no mistakes, no mistakes, no mistakes. If it runs 1,000 examples with no mistakes, you're happy. But the worst case would be that at 999, it's going to make a mistake. I cannot use it. I wanted an algorithm that runs on 1,000 examples with no mistakes. After 999, it made a mistake. Okay, mistake number one. Do it again. Worst case, what will happen? After 999, it's going to make a mistake. I can't use it again. But this is mistake number two. And I told you it's never going to make more than 500 mistakes. So just do this 500 times. After the 500 times, you can keep on running. Now, if you're lucky, a lot earlier, you will have a stretch of 1,000 with no mistakes. But you see, this is the intuition that I want to sell you is if you have an algorithm with guaranteed mistake bounds, you can also convert it to an algorithm that runs for long stretches with no mistakes. I gave you an extreme kind of worst case conversion, but hopefully the intuition is clear. In real life, what we're going to do is we're going to wait. We're not going to wait, but rather we're going to run it. For every stretch like this, we're going to remember how many examples we were able to be consistent with and weigh this hypothesis as a function of this stretch. The longer the stretch, the longer the consistency stretch is, the higher the weight is. And this is going to be average perceptron. So the weights are going to be a function of the length of the no mistake stretch. So here is how it's going to run. So I have many indices here. So M is going to be the number of examples. K is going to be the number of mistakes I'm making. CI is going to be the consistency count, how many examples I've seen without making any mistake. And VI is my hypothesis. Remember, VI is a vector, right? It's my weight vector. Okay, so I have my label data. We think about it as running over the same label data many, many times if M is not large enough. And the output is going to be a list of weighted perceptron or weights for weight vectors. So the weight vector V1 is going to have a weight C1. The weight vector Vk is going to have weight Ck. I'm starting with k equals 0. The vector V1 is 0. The count, the consistency count is 0. And I'm running over the example. Every time I'm computing my prediction, so basically I'm using my perceptron here, sin Vk transpose x. If I made a mistake, I increase the mistake count. If I made no mistake, if I made no mistake, I'm increasing the consistency count. If I made a mistake, I'm updating my weight vector. And in fact, I'm putting it aside. So at the end, what I will have is the list of all weight vectors that I had with their count, right? So when I stop predicting, I remember, okay, V1, I kept it with me C1 times. V2, I kept it with me C2 times, and so on. And my real prediction is going to be based on a weighted sum of these. So when you give me a new example, I'm going to do the dot product with all the vectors that I have in my collection and weigh them by CI. Okay, so I have a weighted perceptron algorithm, and this is an algorithm that has nice theoretical guarantees beyond just number of mistakes. We'll be able to articulate what kind of guarantees they have next week. Now, first of all, the algorithm is clear? Questions? So, in fact, we can do this on top of any online mistake-driven algorithm, not only perceptron. And you're going to do this for three algorithms, three different algorithms, versions of perceptron in homework 2. Now, the implementation requires some thinking. This is part of the homework. The reason is that you may need to keep hundreds of VIs, and if the dimensionality of VI is large, it's going to take a lot of space. So you want to be a little bit clever about how you do this. And this, as I said, this will be part of the homework. Think about it. We gave you this warning, at least, so don't just do it in a brute force way. Questions? Yeah.
How do you pick T?
Okay, good question. So in the homework, I think we're going to give you T. In real life, you need some stopping criteria. And your stopping criteria could be, say you have some set-aside data for development set. You're going to measure your performance on this set-aside data, and at some point you're going to be happy. Say, okay, I'm not going to change anymore because I'm happy with the performance here. You can also invent other stopping criteria based on, I haven't changed my weight vector for a long time, so I might as well stop training. And you can imagine other criteria like this. So in this case, I've written it as if it's a fixed number. In real life, it will not be a fixed number. You will decide on your stopping criteria and determine t this way. Other questions? Okay, so really this is a good algorithm. You will run it on Perceptron, on Winnow, which is a version of Perceptron that we're not going to talk a lot about in class, but you will see it in the problem set, and a third algorithm that I will get to in a few minutes. And really, these are good learning algorithms already, and you will see this later on. Okay, a couple other extensions. So we already got the intuition, we discussed it a couple of times, that thick separators are more robust than thin separators. So you want to be able to not only separate the red from the purple, but also separate them with a thick separator, because you know that in the future, things are going to change a little bit. And if you have a thick separator, you're going to be a little bit more robust. How to accomplish this? We will see other ways of doing it, but if you run Perceptron or Winnow or other online algorithms, one way to do it is to say, you know what, I'm not going to promote or change the weights. Promote and demote are, but when I say promote, I mean increase the weights. That is, you made a mistake on a positive example. When I say demote, I mean decrease the weight. You made a mistake on a negative example. So you're not going to promote and demote only when dot product wx minus theta is less than 0 or greater than 0, but rather choose a small number. You can tune this small number, but you choose a small number and you say, you know, I'm going to be more strict. I'm going to promote not only if it's negative, but even if it's less than something, already then I'm going to promote, and the same here. I'm going to promote if it's greater than something. So you kind of enforce some thickness. Now, if you think a little bit about it, and we're going to get to it when we talk about support vector machines, this gamma here is what is called a functional margin. So once your W grows, that is, you ran your algorithm many, many times on many examples, you've added to W, and W becomes a big vector in terms of size of the vector. That is, you can compute L2 size, sum of all Wi squares. This becomes a large number. The impact of this gamma is going to disappear with time because it's a fixed number. Nevertheless, this has been shown to be a very, very effective algorithmic additions and important to use. I don't think we ask you to do this in the homework, but good to know. Here's another extension that you should think about. Let's assume we run Perceptron. I made a mistake on this example, this purple one there, X. I keep on going. I see the same example again. Will I make a mistake on it? Yes, no? So, if you remember, we gave this example last time, and you should, where is it? We gave this example of how Perceptron works. So we started with this. This was our hypothesis. This is our W. This is Wx equal theta. And we are considering this example. We're going to make a mistake on it. Let's assume we updated W after we made this mistake. If you present me this example again, will I make a mistake? Am I guaranteed to make a mistake, or am I guaranteed to not make a mistake? Thoughts? Yeah?
In this example, you would still make a mistake because, like, the vector pointing to the data point isn't really enough to kind of shift the direction. So you're not really guaranteed to make a mistake or not.
Right. So this is what happened. I corrected by adding x. Right. So this is my x. This is when I added it. Can you see the mouse there? And this is what happens. This is my new hypothesis. Now you can see that on this data point, I'm going to make another mistake. So there's no guarantee. Basically, you don't know if you make a mistake or not. What if you want to make sure that you're not going to make a mistake on this? Any idea? It's really important to me not to make a mistake on this data point. Give me a suggestion. What should I do? Yeah? Okay. How I scale this? Yeah, that's a good idea. And that's going to be our solution. I was hoping for a simpler answer. What I was hoping for is do it again. Right? So if I feed my algorithm again with this example, I'm going to make another mistake, right? You can see it from this. I will make a mistake on this example again, but I will add this vector again, and maybe next time I will stop making. Maybe I will need to do it 7 times. Eventually, I will not make a mistake on it, right? And your suggestion already predicted that and said, add 7 times the vector, which is the same thing, right? So feeding the example multiple times is exactly the same as feed the example times 7. Everything is linear here. If you're not convinced, try to do the algebra and convince yourself that it's the same thing. And basically, this is what this algorithm that I call here aggressive perceptron is doing. Yeah. So essentially, I changed the learning rate, which means I scaled x appropriately. And you can do the algebra. Maybe I did it here in the notes, but you can do the algebra yourself and convince yourself that this R that I chosen here is the right scaling to guarantee that next time I see W, I will not make a mistake on it. So again, any online algorithm, in principle, you can do this, and sometimes you want to do it. So this is just an issue of understanding that you can modify algorithms, and you can you can extend them various ways. So okay, so just if you are interested in this set of algorithms, there are multiple. There's a family of algorithms like this. You can go to LBjava, which is a package that was developed in my group. They have Perceptron, we know, average perceptron, various other bells and whistles associated with these algorithms, which you can look at. Okay, so let's switch gears here and think about the general setting that we're talking about. So we talked about general stochastic gradient algorithms, right? So the way we presented it, we have a collection of examples taken from X cross Y here. And our goal is to minimize this expected risk function, which we call J, which is really the expectation over xy's of this Q function. And we approximate it by the average over our M training examples. Right? In stochastic gradient descent, what we did is we said, okay, we're going to approximate this minimization problem by computing the gradient and updating the weight vector this way. The new weight vector is going to be the previous weight vector minus some learning rate, RT, times the gradient of our loss function. Right? So that's what we did before we started with Perceptron. And in fact, we've done this in our first lecture for a specific Q. But this is the general paradigm that we want to work with. And in fact, it turns out that all the algorithms that we are talking about, or almost all of them, are really versions of this for different loss functions. So let's look at it. Okay, this is just to remind you what is Q. Here is one algorithm that we talked about, LMS, for least mean squares. Again, this is the Q function, this is the learning rate, and this is the gradient. For LMS, we computed the gradient. We figured out that the gradient is here. Okay, you can see the mouse, hopefully. It's this y minus the dot product times xt. Okay? By the way, this algorithm also has a name because it was invented before people thought about it this way. It's algorithm from the 40s or something like that that was called Widrow's Adeline. Notice that this is not a mistake-driven algorithm, right? I'm making changes all the time as a function of the distance or the gap between y and WTX. You can look at it this way. So this is the green curve here. This is my loss function. And except when I'm at the point 1 here, where y times W2x is 1, I'm always making changes. Okay? We can think about another common loss function that is called the hinge loss. And this function should be familiar to you because we just talked about it a few minutes ago. So what is this? Remember, the version you've seen a few minutes ago, instead of 1, add gamma here. And what did we say? We said that if 1 minus this is negative, then the value is 0. This loss function is 0. So look at this line here, the blue line. When I'm greater than 1, when y times w dot product x is greater than 1, my loss is 0, which means I don't make any changes, I'm happy. If I'm below 1, then it starts growing up linearly with this dot product. Okay, so this is the same function that before I called it the slack parameter, the extent to which the data deviates from being linearly separable. So now we are using this as our loss function. We're going to call it the hinge loss function. And let's compute the gradient. Now, really, I have to compute subgradient because there is this corner here at 1 that I cannot compute the gradient for, but forget this point. We can compute to the right of it and to the left of it. And you can see that to the right of it, the loss is 0, no update, right? To the left of it, there is an update. And if you compute the gradient, you will see that the gradient is just x. So my update is going to be just adding x. Either plus x if y is positive or minus x if y is negative. So essentially, what I got here is I got Perceptron back as a gradient descent algorithm with hinge loss. Okay? Again, Rosenblatt didn't think about it this way, even though gradient descent was around long before him, but this wasn't the perspective then. But now we can think about all these algorithms as really gradient descent algorithms. And these perspectives allows us to generalize and invent other algorithms. So here is another stochastic gradient algorithm. Again, I'm putting at the top the general gradient descent algorithm. So far, we gave a couple of update rules. All of them kept R, the learning rate, fixed. But you can also think about changing the learning rate. And this is what the algorithm AdaGrad is going to do. So the idea or the intuition for this is that if I have frequently occurring features in the gradient, I want to be able to sort of eliminate the changes because of them. I kind of got used to them, and I don't want to change frequently. On the other hand, if I have rare features, I want to be able to pay attention to them and notice them and have a relatively higher learning rate for those. Eventually, if they become very frequent, the learning rate for them will also go down. So how do we accomplish this? We accomplish this with adding one more index to the learning rate. So I'm going to have a per feature learning rate. So T represents the example, J represents the feature, and my learning rate for its time T for feature J is going to be a fixed R divided by this capital G square root of. What is capital G? Capital G is the sum of all the gradient so far square. So basically, overall, with this G, this is going to be my update rule now. So it's very similar to the general update rule that you see up there, only that I replaced my learning rate by this R over capital G square root. So let's think about an example here. So the easiest way to think about it is in the case of perceptron and Boolean examples. So if so far until time T, the Jth feature was always 0, fixed, I never updated it, right? Now suddenly it becomes 1. So if you look at this capital G, because until J everything was 0, capital G was 0, now the last one for J and time T equal K, it's 1, sorry. So G is 1, and what I'm going to get here is the first learning rate is going to be, I'm going to add 1 here for lowercase g and 1 for the sum. So the first learning rate, the first time I'm going to make a change for the Jth feature, I'm going to change it with learning rate R, exactly. Now, if it goes back to 0, then this G is going to be 0, so I will not make any more changes for this feature. But if it keeps on changing, then this is going to be 1 all the time. This is going to grow now. So with time, I'm going to, again, stop changing, stop updating the weight on the Jth feature. Or the amount of change in the Jth feature is going to go down with time. So again, if nothing happened on the Jth feature, I'm not going to update it. We know that because if you think about perceptron with Boolean examples, zeros and ones, we know that only the weights of the active features, the on features, are going to change, right? I'm adding x to the weight vector. So all those features for which the value of the feature is 0, I'm not going to change the weights. I'm only going to change weights of those features that have 1. What this one says, look at the, sit on a specific feature, look over time. If it was 0 all the time, you haven't changed it. Suddenly it's 1, you're going to change it with the full step, with R as the step. And from that on, you're going to diminish it. And it's going to go down. So this algorithm, and you know, I describe it here for simplicity in the case of Boolean examples, but it's going to have a similar effect also in the real valued algorithm. So basically, the idea with this algorithm is that it adapts the learning rate based on the data that you see. Turns out to be a very important algorithm or a very important tweak to gradient descent. Some version of it is used today in almost all stochastic gradient descent algorithms. Later on, when we're going to get to stochastic gradient descent algorithm in neural network, you'll see that also a version of it is one of the most popular SGD algorithm being used. And this is going to be one of the algorithms that you're going to play with in the homework. Okay. So you can think about what I said so far, average perceptron. And in fact, also other grad, as a form of regularization. What is really regularization? It's a way to control the changes that I'm making or the expressivity that my final hypothesis is going to have. And the way we formally think about it is I have my loss function, which I showed before. This is this left part of this function here, 1 over m, sum of the loss function over all examples. And I'm adding another component here that I call here Ri of Wi. It's a function of the weight vector. And the idea here is to enforce simplicity of the learned function. I don't want to learn a complex enough, a too complex function. So in the LMS case, when my loss function was this, I have several ways to add regularization term. For example, I can add this L2 term. Remember that this is basically the size of the weight vector. All of you have seen it in your linear algebra, for example. So basically, it's the sum Wi square, where Wi is the weight vector. You can also add what is called L1, which is just the sum of the absolute values of Wi's without squaring them. All these algorithms that here I'm presenting as basically take the LMS loss function and add a term that I'm going to call regularization terms. These are all famous algorithms. Some of them were introduced before we understood this notion of regularization, like ridge regression, an old algorithm, or when I add L1, the problem is called lasso problem. I can do the same thing for other loss functions. If I take this hinge loss, which I introduced earlier, and add L2 regularization, this problem is called support vector machines. Again, introduced as a support vector machine from other perspectives. We're going to do it in about a week or two. But really amounts to this, to taking the hinge loss function and adding this regularization. And you can also think about other loss functions. This is a loss function that was on the graph of loss function that I introduced earlier. It's called the logistic loss. And if you add this L2 regularization, it's called logistic regression. So one issue that I've not addressed at all is the goal is to enforce simplicity. Why is this enforcing simplicity? Basically, what I'm saying, I'm controlling the size. Yes?
When you're penalizing the coefficient coefficients. Basically, you are trying to solve the optimization problem such that the larger the penalty, the smaller the coefficients will be. And in some cases, like lasso, you will actually maybe get rid of some of the variables. So you're getting a simpler model.
Right, so basically I'm controlling the size of the weight vector. One way to control the size of the weight vector is you have a weight vector that is long. Let's say there is a 0.5 on all the weights. I'm deciding that some of them I'm going to make zeros. So it's a simpler weight vector. That's one intuition. So I'm not sure if at this point, beyond saying that I'm going to zero out some of the components, it makes sense that just bringing them down to 0.01 or 0.1 is any simpler than not bringing them down. But what we're going to do is, in about a week or so, we will actually show that a small size weight vector is, in a well-defined way, a simpler weight vector. And it's going to help us actually control the simplicity of the learn function. It's going to be equivalent to learning a thick separator rather than a thin separator. So small size weight vector is going to be equivalent to a thick separator. At this point, we'll just take it for granted. That's what this does. Okay. As I said, it's really the same learning problem. These are all convex optimization problem. The same gradient descent algorithm or mechanism is going to work, only that every time you differentiate a slightly different function. So a very unified way of many, many, many different algorithms. And remember that when I'm looking at this middle case, hinge loss, this is Perceptron, right? We just showed it a slide ago. When I'm adding this loss function, it's called support vector machine or SVM. I mean, really very close relatives. Okay, so let's move on. I already introduced two of the algorithms that we're going to talk about. And here's the third. So far we talked about an additive algorithm. Perceptron is an additive algorithm. I just justified this sentence that SVM is a very close relative of Perceptron. Everyone should agree with that. But there could be other algorithms that have the very similar shape to Perceptron. One of the important members of this family is an algorithm called Winnow that is a multiplicative learning algorithm. So I'm just going to introduce it. I'm not going to spend a lot of time. It's a very interesting algorithm. I used to spend more time on it, but we don't have time. So I'm going to just put Winnow and Perceptron together on the same slide so you can see what happens. So this is, the top one here is Perceptron. I make a prediction by doing dot product. If it's less than the threshold, I'm going to say negative. And if the class label is 1, positive, I'm going to update. If it's greater than the threshold, I'm going to predict positive. And if I made a mistake, I'm going to make a change by subtracting the weight. Winnow is very similar, only that rather than subtracting or adding a constant, I'm going to multiply the weight vector or divide the weight vector by something. The way I've written it here is by 2. In real life, you will not do it by 2. You'll do it by 1.13 or some other small number. But basically, the idea is that rather than adding a constant to the weight vector, you're multiplying the weight vector by something. The impact of it is sometimes quite striking. And you can think about, basically, if you're multiplying something, and you know that you need one of the weights to be very high, because this is a really important feature, you're going to reach that high value much, much faster if you multiply it. Right? Think about it. You want to get, you initialize everything as 1. You want to get to 1024 as sum of the weight. It's going to take you 1024 steps if you're using Perceptron. It's going to take you 10 steps if you're using Winner. Everyone agrees? That's the issue there. And therefore, it's going to be important. I'm just waving my hands here. It's going to be important in cases where just a few of the features are really important, but you need high weights on them. You're going to reach this very quickly. Okay, so we have many algorithms. How do we compare these algorithms? We can think about generalization as one way to compare. Even though all these algorithms that we are talking about are linear learning algorithms. So we know, I'm putting this in, I'm adding question marks there because we don't really know yet, but I'm telling you that all these learning algorithms, because they use the same hypothesis, eventually are going to converge to the same thing. So the question is, how long would it take them, really? So generalization is really, in this case, given that we fix the hypothesis space, a question of how long, how many examples do I need to get to a given level of accuracy? Of course, there's also issue of efficiency. There's issues of robustness, for example, robustness to noise, adaptation to new domain, and so on. We're not going to talk a lot about this. We are going to talk a little bit about how many examples are needed to get to a given level of accuracy. So in order to think about it, it's good to think a little bit about characteristics of the data. What kind of data do we typically see in learning algorithms? I'm going to go back to this example, which we've seen a couple of times already. I don't know whether to laugh or cry. And I want to think about what happens when I take these kind of examples and map them to my feature vectors. How do the feature vector look? So I'm defining a set of features. We already made suggestions, right? The suggestions that were made were sit on a word, look at the word before it, 2 words before it, word after it, 2 words after it, or maybe 3 if you like, and basically define Boolean feature that say, the word before me is chair, the word before me is board, the word before me is monitor, yes or no, Boolean features. So if your dictionary has 50,000 words, you can see that any way you do it, the number of possible features is going to be huge. This is even before I'm blowing up the feature space by looking at conjunctions. The word before me is monitor, and the word before that is D. I'm going to have tens of thousands or more features. How many of them are going to be active in a given example? How many of them are going to be 1 in a given example? Yeah? 6, if I just take the window, right? Very small number are going to be on in a given example. I don't know which one. It's a function of the sentence that I read. So that's 1. 2, how many of them are really important to the decision of, is this weather type 1 or weather type 2? Probably also a few, right? More than 6, but definitely not 50,000. Most of the words do not matter. You can replace the laugh here by any verb. It doesn't matter to the decision. So again, you don't know which are going to be important, but you have the intuition that very few of them are. So that's what I mean when I'm going to talk about sparsity. So before that, I want to just remind you that we're talking about feature extraction here. You already know something about feature extraction. In your problem set 1, you played a lot with feature extraction. In problem set 2, there are going to be two parts. The first part is going to be synthetic data. We basically are going to give you data that was generated. You will read the explanation of how the data was generated. In the second part, you will actually do feature extraction yourself. So good to think about it again. The key point that I want to mention here is that we are talking about words, order of words, sometimes properties of word. Is it a verb or a noun or an adjective? And sometimes we talk about function of these, conjunctions, for example. And we talked about why this distinction is needed. Anyone doesn't know why this distinction is needed? We okay? Okay, this is why it's needed. Or maybe this one, if you remember this example, the idea that sometimes if I don't blow up the feature space, I'm not expressive enough. I cannot learn with linear functions, so we want to do this. Once this is behind us, let's go back to the representation. So we agree that the number of potential features is very large, but the instance space is very sparse. Every example has very few on features, and also the decision depend on very few features. So the function space is sparse. Important to realize that these are two different things. Instance space is the examples. So let's assume we have Boolean examples. Very few of these features are going to be 1. Most of them are going to be 0. And in the function space, which are the W's, most of the features are unimportant. So either the W's are going to be 0 or they're going to be small numbers. And a few of the W's are going to be larger because these features are really important. So we talk about two types of sparsity, and different learning algorithms care about different types of sparsity in different ways. And this is one of the things that you'll explore a little bit in your problem set. So mathematically, when I talk about sparsity in the function space, I care about the size of U or W. If I care about the sparsity in the instance space, I care about the size of X. And it turns out that some algorithms, like multiplicative algorithm, really do well when the U is sparse. And some algorithms, like Perceptron, do better when X is sparse. In real life, both of them are going to be sparse, so the question is of a trade-off between them. I'm quantifying this here in exact terms, but it doesn't matter. You can look at it. I'm giving here an example of extreme scenarios. I don't want to go over it. I want to show you instead a graph that in the limit, this is kind of things that you might see in your problem set. So what do I show here? I show a function that is a linear function, 10 out of 100 out of n. N is the total number of features. 100 is the number of important features. And the function is going to be on if any 10 out of these important features is on. If you think about it, this is a linear function. You looked at the quiz at some of these functions. I'm showing here a graph as a function of n, 1,000 dimensions. In the homework, we didn't give you so many dimensions because it's going to cost a little bit, space and time. But what you will see is that algorithms like we know, their learning curves is very flat as a function of n because they strive when the function is sparse. So this 10 is fixed. N grows. So as n grows, the function becomes sparser and sparser. Relative to the number of features, less features are important. Other algorithms like Perceptron, really, the number of mistakes they're going to make grows linearly with n. So you're going to see, in this case, more mistakes. So you will see One of part of the homework is going to be to generate learning curves. They will not be as nice as this one, but they will be relatively similar, and you'll see differences between algorithms as a function of sparsity. Okay, so let me jump a little bit to the next topic, and because I want to leave you with a small puzzle here. Okay, and here is the puzzle. So next time we're going to start talking about kernels, and one of the important components of talking about kernels is an idea that is called dual representation. So I want you to think about Perceptron from the following perspective. Here is the Perceptron update rule, right? You know this by heart already. I take W, I add yx, plus x or minus x. Now, here is a question that I want to leave you with. Let's assume that I have the following scenario. I saw 4 examples. X1 was positive, X2 was negative, X2 was positive, X3 was negative, X4 was also negative. It so happened that my algorithm, as I went on, made mistakes on X1, on X2, and on X4. What is the resulting weight vector? I started with W. Let W be the initial weight vector. After I went through these 4 examples, I want you to tell me what is my new weight vector. Think about it. Everything is on the board. We'll have to stay here until someone responds. Okay, suggestions. Yeah. I don't know, you tell me. What's the update rule of Perceptron? If I made a mistake, if y prime is not equal to y, what does that mean in English? A mistake. I made a mistake. So if I made a mistake, then I update. So after I looked at x1, what is my weight vector? Yeah?
W minus R times x1?
Let's say R is 1, so W minus x1. After I touched x1, I made a mistake on x1, right? So it's W minus x1. Then I went to x2. Okay, why is it minus x1? Okay, maybe it's wrong though. What do you want it to be? Plus x1, because x1 is a positive example. I made a mistake, which means I thought it's negative, but the Perceptron algorithm says plus r yx. So if y is plus, if y is 1, I'm adding x. So, okay, thanks. So w plus x1. After I see x2, what do I do? So add x to y.
Because you got it incorrect.
I got it incorrect, and it's a positive example. And then I go to x3. Nothing. I didn't make a mistake on x3. And then I get to x4. Minus x4. So that's my next w. Why is this important? First of all, you have to know this by heart, because It's the simplest learning algorithm. You have to realize. Now, the interesting thing here is that you can see that the W space and the X space is the same thing. Maybe you knew this before. And the other thing that you can see is that really my W is a linear combination of my examples, right? My weight at the end, let's assume I started with 0, forget the W at the beginning. My weight at the end, after I'm running the algorithm, is really a linear combination of weight vectors, of examples, sorry. So you have examples here. My W is going to be a linear combination of them. And that's going to be important and will allow us to play interesting game, move to a dual representation. So rather than learning W's and changing them all the time and thinking that we're working in the space of W, we will actually keep the examples and say, well, all the information about W is really here in the examples. You just have to weigh them and add them or subtract them. And this is going to be our representation. This is going to be an important step for something that we call dual representation. Okay, so think about this. We're going to revisit this again on Monday and start looking at your homework. Okay, have a good weekend.
Question. So we talked about the sparse features that we had for in terms of the letters. You have 26 alphabet, we have 1s and 0s. Why don't we just use the location of the letter instead of just, and then normalize it? What do we use like 0s and 1s to say like what is A and what is B and what is C? So let's say you want to see like Apple, for example. A, we have to, for A we have to have a feature.
Okay, first of all,
Yeah.
please ask this question in class.
Okay, yeah. No, I was just wondering, I just came, yeah, I'll ask it next time, but.
So, because, as I said, other people want to know. So first of all, in the example that I gave here, I did not refer to characters. I refer to words.
But if we do characters, let's say, for example.
Yeah, so I can take the position into account. It just will give me more features.
Would it be less? Because if you do characters, you have to do 0s and 1s. So you have, like for A, you have 1, and then you have all 0s, right?
So for A,
You have
so
one and
if
zero.
I have character features, I only have 26 different characters. If I have word features, I have more than 26 words.
Yeah, but
So
if
it
you
depends
use
on the problem.
Yeah, but for last homework, for example, let's
Yeah.
say, we use 26 for each alphabet.
Yes.
Right? We could have just say like 1 for A, 2 for B, 3 for C, all of that, and then at the end, because they go from 1 to 26, just normalize all of them to like a number from 0 and 1. As if, because then we'll now have 390.
But you will never get around it. You want the position. You want to know whether A is in the first place or the second place or the third.
No. Position is fine. So that in Apple, for example, right? We use 1 for A. We use 1 and 25 zeros. Then for P, we use 0s, 1, and 0, right? Yeah. Instead of that, why don't we just use 1? And then for the second one, for P, we use the number and the location. For the second. Instead of just having 0s and 1s, have just the location each other.
So then what is the meaning of the second feature? What is the
P is the location of P. So let's say Apple would be just A, B, P, L, E, all location of all those alphabets. When you run
in the
into each
second
other,
feature you will have 26 values instead of you basically have either 1 over 26 or 2 over 26 or 3 over 26 and so on.
it ought to be 26 just a number.
But
Yeah.
will be 26 values.
1, 3, 2,
Try.
So the feature space will not be 390, we just need the number of alphabets.
Yes, but effectively it's the same thing. We have discrete values. Fine, run the algorithm this way. It's another encoding. See what happens.
You see, there's not really.
No. In the decision tree, it's not going to improve at all, but it's a good exercise. Right. Yeah.
I think I just need your signature there. And then
So you moved into 519?
yes, from 419.
Okay, so you remember that you have to write a proposal pretty soon.
I have to write.
A proposal for the project.
Okay.
Okay, you can add this.
Thank you.
Sure.
Adaptive version of Perceptron where
Yeah.
like it updates the weight depending on how
The
frequent.
learning rate. The learning rate. Yeah.
So is there a reason why we do it like over the square root of the size or?
The reason is that you can prove something this way. So basically that's it. I mean, it works well, and there are theoretical reasons why that doesn't work well. So I can give you a pointer to the paper that did that. In fact, we will add it to the web. And yeah, it's a good question, but it's going to take 30 pages to argue that this is the right way. But if you're interested, yeah, it's a good question. And it turns out that it's work magic. You'll see in the homework. It's a really good algorithm.
So in the end, when you're adding x1 next to minus x4, why didn't you take consideration?
I just assumed it's one. Just for simplicity.
But if it wasn't,
It would be 2 times.
So before we begin, if you're... There we go. Before we begin, if you're seated directly next to somebody, would you please move over so there's a space between you? Which may necessitate moving rows.